Hi, I'm Wesley Chen, and my project was signal avoidance using 5G. Okay, so what does that mean? So the idea is we have a bandwidth that we're allowed to use for 5G, but we want to expand this bandwidth in order to have more channels so we can connect to more devices and just send data faster in general. However, there's going to be some legacy usage of the spectrum that we have to avoid. So the idea of this project is to develop the framework to test various signal avoidance techniques, which would allow us to not interfere with those legacy signals. Okay, so first, the devices that we used. So on the bottom there, we have the signal generator, and how it works is on our personal computer, I have just a Python code, and using that Python code, I can write a waveform file, which is like kind of, if you think about it, it's kind of an audio file. But anyways, I upload that to the machine, and it sends that to the oscilloscope, which then I can download the data to analyze. So first of all, what is a signal? Just now I mentioned that all radio signals are like kind of like audio, and that's like kind of exactly what it is. There's a lot of similarities between radio and audio. So you can, for now, you can think of a radio signal just like an audio signal. So if you zoomed into that audio signal, you might see something like this. And you might be thinking to yourself, well, that looks exactly like a sine wave. And that's exactly what radio signals are. So radio signals can be thought of as combinations of various sine waves. So for example, here we have a kind of slow sine wave on the bottom right, and then a faster sine wave on the top right or top left, and that would combine to give us a signal like this. Now, because of this property that every signal can be thought of as a combination of sine waves, and each of these sine waves has their own properties, for example, frequency, which is how fast they go up and down, and phase, which is where it's centered. So both of these are centered at 0, but they could have been centered at 1, for example. Because of that property, we can represent every single signal in terms of those frequencies. And that's what we call the frequency domain. And it's an equivalent representation. And how conversion from time domain to frequency domain works is, sorry to get into the math of this, but basically it works by taking every single possible frequency of sine wave and multiplying that to the signal, and then take the integral over one period, and that tells you how much of that specific frequency is in the signal. Okay, so normally we think of signals as in terms of time, right? So at some point in time, it might be here, and then it goes up and then down and up and down. But actually, every single signal has another dimension to it. So this time, I guess representation, that's this graph, but if you looked at it from the top. So every signal has a second factor to it, and we can think of it in multiple ways. One way is to think of it as amplitude and then phase. Another way to think of it is a coefficient of cosine and sine. And the last way to think about it is in terms of complex numbers. And the reason we do that is because it simplifies a lot of the math that we have to do later. So now we have this graph in 3 dimensions, but a lot of times it's hard to think about things in 3 dimensions. So another thing we can do is just look at the graph from the front view, and that give us something like this, which is called the IQ plot. So we take every single point in this 3-dimensional graph, and we take its coordinate across this side and coordinate across this side, and we compress that all into this 2-dimensional graph where the real part of the signal is on the x-axis and the imaginary part is on the y-axis. So now getting into modulation. So what is modulation? Well, when we send a signal, we can only send it at some very slow frequencies. So if we want to send stuff at higher frequencies, then we have to do something called modulation. And how it works is we take our signal and we take the real part and multiply it by a sine wave of the higher frequency, and we take the imaginary part and multiply it by the cosine wave of the higher frequency. And that gets us our new signal that we are supposed to transmit. Now, it's important to note that this signal is always real. There's no imaginary component to it. And that's because we can't send an imaginary signal because it's imaginary. So that's an important factor that occurs during modulation. So just one simple example of modulation. Imagine initially we have a square wave, and this square wave doesn't have imaginary part, and it just switches between -1 and 1, -1 and 1. And then we have our carrier frequency, basically the sine wave at that higher frequency. And now if we do the modulation, well, we take that -1, we multiply it to the sine wave. We take our 1, multiply it to the sine wave. And what that's going to do is we're just going to flip up and down. The sine wave is just going to keep flipping up and down over and over. So this is actually exactly what BPSK is, which stands for binary phase shift key. It just means that at each of these symbols, you can only send one bit at a time. Other methods such as QPSK or QAM, you can send multiple bits per symbol. And another special property of BPSK is that when we look at our IQ plot from before, so if you remember, each signal has the real and imaginary parts. Well, for BPSK, we don't have an imaginary part. You can only have I equals 1 or -1, and Q is always 0. So if we do all those steps and then we kind of like reverse it, then we can get our BPSK signal. And this is the frequency domain of that signal. And you can see I sent this message hi with 3 I's, and I get that exact message back. Another way we can send signals is OFDM. OFDM stands for orthogonal frequency division multiplexing. And the idea is that for BPSK, we had this whole bandwidth for to send signals with. Well, for OFDM, we're going to take the bandwidth and split it into smaller sections, and each of those is going to send a little bit of data. And you might be thinking, well, now we can send bits faster, but actually no, because each of these bandwidths is smaller, and that results in the fact that you can send bits slower on each of those individuals. So the actual bit rate is still the same, but there are some advantageous properties that we like about it. So when I said we could transmit BPSK and like kind of do the reverse to get our signal back, I was kind of lying, because we also have to do something called demodulation. So basically, we get our signal, which is the real part times sine wave and the imaginary part times the cosine wave, but we have to get those I of t and Q of t back. And the way we do that is we multiply it back again by the sine wave, the higher frequency, and then we do a low pass filter, and that gives us our real part. And if we want the imaginary part, we do the same thing, but with cosine. Now, if we do that though, you might get a plot like this. And remember, I said it has to be just 1, 0 and -1, 0. This is clearly not that, right? So what went wrong? Well, the thing is, we don't know the exact frequency of the sine wave that we have to multiply by. Even though our machine might tell us you have to do 1 gigahertz, it might not be exactly 1 gigahertz. It might be like 999.9 megahertz, and that's not right. And you also don't know where your signal starts. Like, do I start measuring my signal right now or 10 seconds in the future? I don't know. So, but we have a simple solution to that, and that is something called Barker codes. So that's a kind of random signal, but the thing is our receiver and transmitter both know what the signal is. So then when we receive our code, we can take our Barker code and just compare it along the whole thing and find where it is. And you can see that might be the Barker code, for example. And how it's actually done is a mathematical function called correlation. And that tells us, okay, we have one Barker code here and another Barker code here. So now that we know one Barker code, well, now we know where our signal starts. And if we know 2 Barker codes, well, now we know the frequency offset because we know the time difference between those two. And as a result, because we know the frequency offset and the phase offset, we can use complex numbers. This is why complex numbers were so useful, because they're very easy to correct all of our IQ samples with. And now we get a cleaner graph, which is mostly horizontal. And that's actually how we read the high. So we can do a similar thing for the OFDM, and I get a message, hi WINLAB back. But that's like not really the goal of this project, right? The goal of this project was to see how signals interact. So what we're going to do is we're going to take the OFDM and say, remember, OFDM has these multiple carriers, but we're going to tell the OFDM, no, you can't use those specific carriers because we're going to put the BPSK there. And this is just like kind of flowchart for that process. And you can see now we have the BPSK right there, that bump in the middle, and then around that is the OFDM. And now we can still read our BPSK perfectly fine. We still get our message hi, but for our OFDM, we get some garbage, H, because there's some interference between the two signals. And specifically, the interference works as BPSK is mostly unaffected until the OFDM is around the same power level, and OFDM is mostly unaffected until the BPSK is around 2 times greater than the BPSK, or yeah, than the BPSK. Okay, so in the future, this framework that I built can be used to test different signal avoidance techniques. One of simple example is just adding a buffer between the two signals. And that's pretty much everything that I learned over the course of this summer. Thanks to all of WinLabs and especially my advisor, Professor Prijak.